All right, let's get started. This is lecture 9 in steel design. We're pre-recording this lecture because I'll be out of town on Monday. What should be done by this lecture is I'm hoping homework 2.3 is graded. I'm not sure. Homework 2.4 is probably currently being graded. Maybe they're both graded. I don't know. We'll see how the weekend goes with my TA. But in any case, by Monday, these two solutions will be posted. Homework 2.5 will be due, and 2.6. Of the last lecture, we introduced the method for design, and I think you'll find it's pretty straightforward. What I want to do in this lecture is just go through the process step by step. Let me move my microphone over here. Okay. So what we're going to do is we're going to go through the process of design again. I'm going to go through the slides again very page, and then we'll have an illustrative example here in a bit. So just to make sure that we're on the same page, again, we're still using LRFD limit states and whatnot, so nothing has really changed there. We are still right now only considering these two limit states, gross section yielding and net section fracture. Again, we're going to add a third limit state, block shear, to this later. But we're also, one thing I guess it's worth mentioning now is that we are not going to be introducing block shear as a design component, if you will. Block shear is never really something that influences initial member selection. It's usually something that's just checked later. But that'll become clear as we talk about block shear later on. In terms of design, again, so we in our last lecture, we set up the ground rules for what we're going to be doing. That ultimately, right now, what we mean by design is selecting members to safely resist loads as opposed to being given members and to assess their performance. We're always going to be worrying about the lightest member, at least in this course, and I discussed in the last lecture some exceptions to that, in the real world, but for the purposes of class, we're always going to be using the lightest members. And we're always going to have some constraints in the problems to ensure that we all arrive at the same answer, and that will be the case with this example that we do here in a second. We derived the expressions for our limit states. I think my camera is cutting off one of them a little bit, but we have the gross area design requirement and then the radius of gyration requirement. Those are closed form. We can solve for those and just pick a member that meets those requirements. But the issue with net section fractures, we really can't do that. There's too many unknowns. So what we do is we assume that the effective net area is 75% of the gross area. So again, gross area goes to net area, and then net area is adjusted by the U value to get effective net area. So there's a lot going in that assumption, but it's simple, and it will allow us to initially select a member. But what's critical is that once we select that member, we must analyze it, we must assess it, because we have to verify those assumptions. And so the way that we select our member is we use our gross area requirements. Before, we were just looking at yielding. Now we're looking at yielding and fracture. The denominator of that fraction, we take the minimum of those two terms, because the minimum of those two terms is going to yield the worst case area requirement. So here's our process. We factor our loads, compute our two design values. We then, based on those problem constraints, and these two values, select the lightest shape available. We then analyze that shape and then summarize the results and compute the efficiency. And we talked about efficiency. Efficiency is just load over resistance. The idea that we want that value to be as close to 100% as possible without going over. We're going to be doing a problem here in a little bit where I believe the efficiency is about 96%. We'll see that at the end. And so that's fine. You don't need to pick the next one to try and get that better. In fact, if you probably did, that member probably doesn't work. On the flip side, if you're doing a problem and you have like a 70% efficiency or 60%, your design's probably too heavy. And you probably need to pick one that's lighter. So let's look at the example that we're going to be doing. We're going to be selecting the most economical C shape, so the most economical channel. That's the sort of the constraint that we're putting on the problem, because there aren't as many channels in the manual as there are W shapes. In fact, there's only one page of channels. And so we're going to be selecting a channel to be used as a 21 foot long tension member. We have a dead load of 100 kips, a live load of 120 kips. And so we're going to be selecting a member to resist those loads. We're going to be using this sort of connection configuration, and so we've been given 6 bolts, 3.5-inch spacing along the longitudinal direction, 4 inches along the transverse. And again, note the constraints in the problem. We're restricted to selecting a C shape, so that's going to ensure that we all arrive at the same member. So let's get right into it. Let me pull up the notebook. Okay. So let's see if we can start off by going through some values, or to establish some things that we know are going to be constant. So one of the things that we do know is constant is our material properties. Okay, so our material properties, we know we're going to be doing, or we're going to be using an FY of 36 KSI and an FU of 58 KSI. And, again, we get that from table 2-4 because, if you see, we are using grade 36 steel, so that's pretty straightforward. And again, I think probably, starting now and throughout the course, we're going to hit a point where some of these values, like we're going to kind of just know, like for grade A 36 steel, we know 36 KSI and 58 KSI respectively. So it'll be kind of quick as we move forward. I'll also list some member properties. I will say member and connection properties. So we know that the member for this problem is 21 feet long, and I'm going to go ahead and convert that to 252 inches because we are going to need that for LRR computations. And we do know that the bolt diameter is, again, our trusty 3/4 of an inch. So we know that our effective hole diameter is 7/8 of an inch. Okay, and I think that's all that's consistent, I guess, that throughout the problem. So with that, let's go ahead and just jump right into it. Let's do a tension member design. So I'm going to scroll down a little bit to give me some room, and I'm kind of showing some of my cards here a little bit because I've got a screen clipping from the my manual subscription and whatnot. But let's go ahead and get right into it. So step 1 for a design is going to be compute the factored load. In other words, we have to know what we're designing for. So we know that we were given a dead load of 100 kips and a live load of 120 kips. And so we have our 2 load combinations, the 1.4 dead and the 1.2 dead plus 1.6 live. But I think we can kind of look at this and know that the 1.2 dead plus 1.6 live is obviously going to govern. It's going to give us a larger factored load. So 1.2 times 100 kips plus 1.6 times 120. And we're given a PU of 312 kips. Boom. That's pretty simple. So now let's do step 2. And so step 2 is going to be, we're going to compute our design parameters. Okay, so the way that I like to do this is, let me scroll down a little bit, give myself a little bit of room. The way that I like to do this is over here off to the side, what I'm going to do is I'm going to compute 0.9 FY, and I'm going to compute 0.75 squared FU. Okay, so let's do the first one. So 0.9 times 36 KSI, and when you chug that out, you get 32.4. Let me move this real quick. So 32.4. Oh, I put that on the wrong line. And now the 0.75 squared, remember the reason that there's 0.75 squared is one of them is our phi value and the other is for the area assumption that the effective net area is 75% of the gross area. So there's two 0.75s there, don't forget. And so when we chug that out, we get 32.625. Okay. And the reason I do these off to the side is because our, let me move this down a little bit. The reason that I do these off to the side is because our gross area design parameter is PU over the minimum of these. Which is 312 kips over the minimum of these two. And the minimum of these two, you can see now that I've done them on the side, is this one right here, right? So which is, when you chug that out, 9.63 square inches. Now, one thing that's worth mentioning is that if you look at these two, I have the minimum of 0.9 FY or 0.75 squared FU, and the minimum was 0.9 FY. So that might make you think, does gross section yielding govern? Well, the best answer is probably, but we're not sure, because the only way we're going to be sure is if we actually pick a member and then assess it. Remember, there's a lot of assumptions built into this, so we have to make sure that we assess the member at the end of the day. That's why step 4 is, as we're going to see, is so important. Finally, we do need also a R design, which is L over 300. Remember, I already converted the L to inches. It was 252 inches. And so when we chug that out, I get 0.84 inches. Okay, so let's just sort of write these two parameters over again and make sure that we're clear. So we have AG design is 9.63 square inches and R design 0.84 inches. Boom. Okay, so these two parameters are going to be the parameters by which I actually select a section. And so the idea is to pick a section that has at least these values, if not a little higher, because I certainly want to pick a member that has, let's say, a lower cross-sectional area than that, because if it has a lower cross-sectional area of 9.63, it probably doesn't have enough capacity to resist the loads. Remember, the gross area is the gross area. This AG design is how much gross area we need to resist this 312 kip load. So it's got to be at least this, if not a little bit bigger. So I'm going to move this down a little bit further. And so I think that's probably good. So now we're going to select a trial shape. All right. So what I'm going to do here, if you can see, I've got a snippet of the manual here, and remember, we're looking for an area of 9.63 and an R value of 0.84 inches. So let me break up my highlighter here. Let's first off, let's look at the areas. So what we're going to do is we're going to find a shape that has at least 9.63, if not a little bit more. So for example, if I'm looking over here on the left, for example, let's just take the C10 by 30. Well, that isn't going to work because its area is 8.81. That's not enough. It's not going to have enough capacity, and it's going to fail. So that member doesn't work. So let's see. What about the 20.7? That's not going to work. That's not going to work. What about the C15 by 33.9? It has a cross-sectional area of 10 square inches, right? The next one smaller only has a cross-sectional area of 8.81. So I obviously couldn't select this member because it's too small. The next highest one up is a viable candidate. So I think that's the one that we should pick. But let's also check the radii. Let's check the radii of gyration. So let's extend that over. So, and I'm going to use my pen here to sort of highlight the key values. So here's that. And let's look at our two radii of gyration. So here's that, here's that. So first off, we see that the radius of gyration in the y direction is the smaller one, and so that's r min, and it's 0.901 inches, and that's bigger than r is 0.84, so that's good as well. So I think the C 15 by 33.9 is a good trial shape. So we're going to say try a C 15 by 33.9. Now I say try because I don't know if this is going to work. Remember, I'm making this selection based on guesses for the net section fracture. That 0.75 squared FU, there's a lot of assumptions built into that. So we have to assess this shape, okay? So step 4 is going to be analyze the C 15 by 33.9. And so in order to do that, I am going to need a few additional properties. If you remember, let me scroll up. Let's look at this. What other properties am I going to need? So, here's the channel, and I have bolts going through the web. So I am going to need the thickness of the web. I'm going to need TW. And then from a shear lag factor perspective, I am going to need X bar. I'm going to need that distance, so I'm going to need X bar. So if we go down here, we go back here to this, I am going to need a web thickness, which in this case is 0.4 inches. And I'm also going to need X bar. And so let me see if I can do a little bit of a better job here. So I'm going to need that and that. So 0.901 inches, 0.788 inches, etc. For the sake of doing my slenderness check, I'm not going to use RX because I know that RX is not going to govern. So, okay, let's now do our analysis. So let's go ahead and write the properties for this trial shape. Okay, so let's do some analysis. And for this, let's recognize, so we're going to compute a gross section yielding capacity, 0.9 FYAG, and a net section fracture capacity. Now, if I go back up to the problem parameter here, how many holes am I going to be subtracting from the gross area to compute the net area? I'm going to be subtracting 2. Because again, if I look at this from a cross-sectional perspective, there's only 2 bolts going through the web. And no stagger factors, so that's a little bit of an easier path to go towards. So I think the analysis is actually going to be pretty straightforward. Also, because this is a channel, I'm only going to have one case of shear lag, and that's case 2, 1 minus X bar over L. How long is the connection? The connection length in this case is 7 inches. So, all right. Let's get to it. So that part's gonna, I think, go pretty quickly. So first off, the net area. So the net area for this problem is the gross area minus 2 bolt holes. So 2 times the hole diameter, and then we are connecting that through the web. I don't need their parentheses there. And so when you chug that out, you get a a net area of 9.30 inches squared. For shear lag, there's only going to be one case for this channel that applies, and so that is going to be case 2. And so for this, X bar is in this case X bar for the channel. So 15 by 33.9 over LCON. So 1 minus 0.788 over 7 inches. And in this case, that comes out to be 0.887. Okay. So now what we can do is we can look at our limit states. So we have gross section yielding. So VPN is 0.9. FYAG, so 0.9. 36 KSI, and then the gross area was 10 square inches, and so that is 324 kips. And then for net section fracture, same as before with analysis. And so when you chug that out, you end up getting like 358.8 kips. So between the two, which governs? Well, that's the one that governs. But are we good? Well, what was the factored load? The factored load was 312 kips. So we are good. And I'm going to do a summary here in a little bit because I think that's a very important aspect of the problem. But there's one final thing I do want to check, and that's slenderness. And that is L over R min. In this case, L over RY, which is 252 inches over 0.901. And so when you chug that out, you get 279.7. So are we good? Well, let's summarize everything. Let's just make sure that we're good on this problem as a whole. So I like to do a summary. In fact, step 5, I really sort of treat as a summary of the problem. So this is something I do want you all to start to get in the habit of, because we're going to have problems later on where we do a lot of iteration. For example, columns, we do a lot of iteration to find the best choice. And there are some instances in beams where we do a lot of iteration on selecting the most economical member. And so I like at the end of the day to put a summary of how things are going with this problem. What do I mean by that? Well, for this problem, we are designing for a factored load of 312 kips. And we selected a member. That member has a VPN of 324 kips. And I'll go ahead and put the controlling limit state was gross section yielding. Now, I also think it's a good idea to put the L over R just to make sure that it is clear. That's okay, because it's less than 300. Now, what I do want to do over here off to the side is compute the efficiency, which is PU over VPN, because what this is telling me is that I know that the member's good. I know it has more capacity than it does load, but how good is it? Well, when you chug that out, you're going to get something like 0.963 or 96.3%. 96.3% is certainly good enough. So much so that if you picked the next one down, more often than not, that member's not going to work. For this course, if that efficiency rating is ever 90% or higher, you can go with that member, and that's going to be completely fine. And most practicing steel designers are going to do the same thing. So let's just summarize what we're doing with this problem. The whole point of this problem was to select a member that can economically resist this load. And we have found the most economical channel that will safely resist this load. So what is the answer for this problem? Here's the answer. That's the answer. That's the member that we're going to use. And that is the basics of tension member steel design. So hopefully that makes sense. What we're going to do is I'm going to give you an assignment on this problem, and we're probably, just like with analysis of tension members, we're going to do yet another example, one that's a little more involved on Wednesday, just to make sure that we're comfortable with the design process. So that's all I have for everybody. I will Wednesday, and I will see you all when we return.